then it doesn't mean that n squared equals to n cubed. The fact that both of them equal are that we are using the equal sign. There is a reason that we are saying T of n is and not is equal to. But it's not really equal. Saying T of n is order of n squared is just a shorthand to this long speech that I gave earlier. Next notation, we say that T of n is big theta of 1 or big theta of n squared or big theta of n log n if you can come up with 3 constants this time, C1, C2, and N0, such that for any input which is at least N0, T of n is no more than, say, n squared times some constant, but also no less than n squared with a different constant. For example, merge sort, if I'm talking about merge sort about say, merge sort, then T of n for merge sort is at most a 5 n squared, and at the same time, no smaller, larger, no less than a third n squared, because it's still, sorry, talk about about a swap sort. So to make it for merge sort, n log n. It does, theta just means to say that T of n is theta of G of n, just means T of n is order of n squared, and also T of n is omega of n squared. It is n squared is the correct answer. Up to me playing with constant, the running time is not less than n squared, not more than n squared. Tight bounds. Okay. So just to reinforce this point, if I'm saying that Qn is order of n squared, then it is also true from this claim. It's also true that Qn is order of n cubed. It's also true that Qn is order of n to the 3.5. Qn is also exponential in n, 2 to the power. If this is true, then all these claims are true. It is true, can I claim, knowing this part, can I claim that Q of n is order of n squared root n? Maybe yes, maybe no, but it doesn't imply, this doesn't imply this. However, if Q of n is omega of n squared, not less than n squared, then it cannot be that Q of n is order of something that goes slower than n squared, order of n to the 1.5. Cannot. But because no matter which constant you're using, n squared, C1 n squared will be at some point larger than C2 n to the 1.5. No matter what two constants you pick, at some point this algorithm will be more expensive than this algorithm. Okay. Now, the big difference between order and omega is that when we are talking about order, we'll also talk about some algorithm in mind. Omega, sometimes we will talk about a specific algorithm. Swap sort, where we are replacing pairs, is an example of something that runs in worst case of n squared, but you can do sorting better. Sometimes the omega refers to a problem in general. But wait. You have n numbers, you want to sort them. What's the best algorithm if these are integers? This station?
Quicksort. Quicksort?
Don't know.
It's a newer version of something like
I mean, and you were right about Quicksort. Quicksort, I don't know. I'll check it later. If there are integers, let's say that these are integers with only 5 digits at most, with some specific range. Very good. Quicksort runs in linear time, but it doesn't work well with real numbers. Now, there is problem with reals, but if the numbers are not of very specific range or not just integers, then Quicksort does not work well. Show me hands, how many of you have studied Quicksort? Okay, maybe we'll have time to discuss it a bit. It's beautiful, beautiful algorithm, absolutely ingenious. But if the numbers are actually real values or just anything but integers of small range, then any algorithm for sorting takes omega of n log n. What does it mean? I just wrote an algorithm for sorting, and the first thing that my algorithm does is check if the array is already sorted. If it's already sorted, then my algorithm does nothing, and it takes linear time. All great, but for other inputs, it will take at least n log n. And the theorem that we have here will say, no matter which algorithm you have, you work hard and came up with fantastic algorithm, and me as a vicious adversary studied your algorithm very carefully, and I'm able to design one input of size n, no matter what n is, for any value of n. I'll be able to generate one input that your algorithm is not very fast on. I'll be able to generate for every algorithm, I'll be able to match it with a bad input that causes the algorithm to run in at least omega of n log n, not faster than n log n. Here's another famous example of a problem that have lower bounds. Let's talk about the element uniqueness. You have an array, and in this array there are n keys, and I want to determine if there are any pair of keys, any key that appears more than once. (17, 3, 9, 17). Hundreds, the algorithm should say yes because 17 appears twice. So it's there are elements that appears more than once. The algorithm should say it's not unique. If all the numbers are different, the algorithm should say they are all unique. How would you solve this problem? N squared trivial, compare each element to each other element. Duh. N squared is trivial. Something better?
Iterate over it, add them all to a hash set, check the size of the hash set against the end of
Fantastic answer. Hashing will run in linear time, expected linear, which is a great example that why randomness works sometimes much faster than anything that you can come up deterministically. What happens if I want algorithms that always runs better than n squared? Then just check all pairs. But hashing is by far the correct answer. But if I want deterministic algorithm, hashing throws coins, right? Where does hashing throws coins? And we'll talk about hashing in this course. But then throws coins is deciding about some constants that you are doing multiplication with or shifting and you need this randomness. And we spend a lot of time talking about hashing. Okay, anyhow, a deterministic algorithm.
First sort them and then.
Absolutely. Sort the elements in, say, merge sort in n log n.
And then scan from the.
So, which means that this problem has an order n log n algorithm.
Either we can do like take pointers on both the sides and traverse them.
I didn't ask if the first element is the one that appears twice. I'm asking if there are any elements. Is there any elements that appear more than once? Okay, so it's not for one element, it's linear time, yeah. So, yeah. So this is one of the problems that has a lower bound. That is, any algorithm that solves element uniqueness should take at least n log n time in the worst case, including hashing, by the way, except that in hashing you could argue that the probability that it takes n log n is very low. Okay, and of course what I didn't list here, but you all know, is that what do you expect about the TSP, traveling salesperson, visiting, and you're getting a map and they want to visit all the cities in the shortest path possible. Well, nobody knows for sure, but there are strong evidence that it takes at least exponential running time. There are arguments about exponential and what, and there are improvements, but there are at least evidence that it's probably exponential. Okay. Here are a few examples that encapsulate most of the math. Lots of the cases that we see in this course, so I'm going to step through these examples. And so, by the way, it's not from the textbook. I don't know if they appear anywhere. I'm using these examples, I think. Since I was PA, which I was, I think, before most of you were born, and using the same examples. Okay. Here n is just a parameter. It's not really the input size. It's a recursion formula. And what does recursion formula? Recursion code, pseudocode does. If n is smaller than 1, do not anything. Otherwise, print 1 star. Probably you can do print 1 star in constant time, and call yourself recursively with the value of n minus 1. This gives us a rise of recursion formulas, which is what? T of n is constant plus T of n minus 1, or the value of n. Just an example of recursion formula, where if we get all the way for T of 1, it's a constant. Some people like recursion formula. I refer you to the master theorem. That helps to solve many recursion formulas. For the ones that I'll show in this course, being much less excited about recursion formulas, I'll try to avoid them if possible, because somehow they kill my intuition about my problem. The problem, but let's see how do I still handle this recursion formula directly. What is T of n? It's just based on the definition, some constant. What constant? To call all these pieces, to print 1 star, to check these conditions, that takes a constant time, plus call yourself recursively with the value of n minus 1. The iteration method will say, okay, let's try to understand what is T of n minus 1. It is just a constant plus the T of n minus 2. What? Let's rearrange it. This is 2 times this constant plus T of n minus 2. What is T of n minus 2? It's same constant again plus T minus 3. And at this point, I start to understand what's going on. So let's pick some value of k that is smaller than n. What happens when I call this function of t of k? It will be k times c, or actually when I'm picking k to be n, for any k smaller than n, for any arbitrary k, all I'm getting from this formula, what happens with the c? I'm collecting k times this constant, plus left with t of n minus k. If you believe me so far, put k to be n minus 1, and what you get? N minus 1 times the constant plus t of 1. What did we say the t of 1 is? It's just t of 1 is a constant once again. Maybe it's a different constant, I don't care. We don't have respect to constant, which is a constant times n, linear in n. Okay, you all knew that it's linear in n, that's fine, but it's a way to formalize your intuition. I'll give you a couple of questions about to play with this, but it's really not. Don't get the wrong impression that the course is about recursion formulas or solving such math E6. That's really not the idea. Slightly more interesting problem. We only got n is the input size. Say if n is smaller than 1, then we can do absolutely nothing. Otherwise, print n stars. For I from 1 to n, print n stars, actually n minus 1, don't care. It's the type of error that I don't care if it's n or n minus 1. And call yourself, just as before, with n knowledge of n minus 1, recursively. What's your recursion formula right now? Q of n equals Q of n and 1 minus 1, like in the previous slide, but instead of the constant standing alone, now it's a constant times n. But because of the n stars that way. Assuming to print a star takes a constant time, so to print n stars, n asterisks, it takes n times this constant. Playing with the same arithmetic, what happened here? Q of n is C of n plus T of n minus 1. Let's reiterate. What is Q of n minus 1? It's constant times n, constant times n, but now I'm just running up to n minus 1. So it's constant times n minus 1 plus Q of n minus 2. What is Q of n minus 2? Constant times n minus 2 plus Q of n minus 3. What happens k steps into this recursion? You're getting C times n plus n minus 1 plus n minus 2 plus n minus 3, dot, 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 plus, if you're going all the way to n to k, all the way until C times n plus n minus 1, n minus 2, n minus 3, all times is constant, or the stars that you printed so far, plus you're calling yourself recursively with n minus k minus 1. And that will be true for any k that is smaller than n. So what happens when I get to the n? When k is n minus 1. What do I get here? It will be this constant times n plus n minus 1, n minus 2, n minus 3, and all the way up to 1, plus Q of 1, which is a constant. Let's read this sum that's written here from right to left. What do we have? 1 plus 2 plus 3 plus 4 plus 5. What you see right here? Just the arithmetic sum. 1 plus 2 plus 3 plus all the way up to n equals to n times n plus 1 half. Times the constant, meaning that this algorithm runs in theta of n squared time. It prints theta of n squared stars. It runs in theta of n squared. Not more than n squared, no less than n squared. Some people start to look unhappy.
What's the difference between omega, theta, and O of?
All of it just says it's my way to convince that the algorithm is not very slow. I don't know exactly what's the running time of this algorithm. Maybe it's case dependence, maybe I'm not smart enough to run the whole analysis. Order says it will not run in more than n squared. It will not run in more than n log n. It's not run with more than, and I'll tell you no more than this number. Omega says it runs in at least this number, at least n log n. This code, no matter what it is, runs in at least n squared time. Hopefully everybody agrees. It runs in at least n squared times a constant. What is this constant? There is some noise here. This constant is half, and it's actually not n, it's n plus 1. But again, it's all constant that vanishes in the big O and the big omega and the big theta. Now, since it's both order, it doesn't take more than n squared, and it doesn't take less than n squared, no matter what is the input, then we can say it's tight bound. It's exactly n squared.
Can you give me an example of the n that it has different order between the upper and lower?
The moment if I'll say that I'm not good enough to analyze the algorithm, and I can say some algorithms will not run in n cube, but especially if the input is not just a number n, but actually there are elements in your array.
I see.
Okay, slightly more interesting example. And I said, I picked these examples so they cover a lot of the math that we did later. For an input of size n, set k equal 1 as long as k is smaller than n, do k equals 2 times k. And I'm asking what's a one time. And to analyze the one time, look at the value of k. When I just start, k equals 1. What happened after executing this command the first time? K equals 2, which I'll write as 2 to the power 1. Another iteration, k equals 2 to the power 2, also known as 4. Another iteration, 2 times 4, making it 8. I'll write it as 2 to the 3. After i's iteration, what is the value of k? It's 2 to the I. How far can I get along with this process? I'm doing it only as long as k is smaller than n, which I'll let you go check at home, go in detail. But it's easy to show that the running time is order of log n. You cannot multiply 1 by 2, 4, 8, all the way up to reach n. How many times did you multiply this number by 2? At most log to the base 2 of n time. And by the way, when you check the log formula, if you remember, log of a times b is log of a plus log of b. Similarly, what happens when a to the power of b, b goes to the b before the log, and so on. So if I write that it's order of log 2 of n, then I can also write that it's order of log to the base 10 of n, just because changing from one base to another, log to the base a of x is log to the base b of x divided by a constant, and we don't care about constants. So when I write that it's log to the base 2 of n, I can write it's log to the base of whatever you want n, or just don't write the base at all, just log n. Questions about it?
Is it the natural log or the log base 10?
I don't care. Here, in the analysis, I showed that actually the number of iteration is how many times can you keep on multiplying k? What will be the value of k? Well, k is smaller than k is equal to 2 to the I, which is smaller than n. Take log to the base 2 from both sides. Here we have 2 to the I. Here you have log of n. Take the I to be before it, and you got a number of iteration j. It's j here, sorry. After j iteration, it's 2 to the j. So j is order log to the base is not more than log to the base 2 of n. And because we don't like such long sentences, we just say it's order of log n.
So in some examples, you are taking out O of n complexity, and in some examples, you are taking out theta of how you are deciding in this we are gonna count or calculate theta notation complexity. Is it?
So here the order and the omega, because n was so boring, it's just a number. Here the order and the omega are both the same. So it's theta of log n, actually. The previous code was theta of log n. Okay, I need help with this code. I think that it's pretty cool example. Not recursive. I have an outer loop that goes from I in 1 to n. I have an inner loop that goes from j start at I, j smaller than n. But notice notice what happens to j. Let me write this other code for a moment. For I equals 1, I smaller than n, I plus plus. for I goes from 1 to n, for j goes from 1 to n, print star. There is no doubt that here it runs in theta of n squared time. Right. I think that you all agree. But the difference here is that here I'm changing j at each iteration by adding 1 to it. In this example, I'm adding to j I at each iteration. So, does anybody know what's running time? It's not a trivial question. So it is definitely true that it's order of n squared, right? Because whatever happens, if I add to j 1 at each iteration, then it's order of n squared, so it just means something maybe happens earlier, but order of n squared is an upper bound. So maybe that's a good answer to your example. You already know that it's order of n squared, and it's absolutely true answer. But it is also true that it is true or false. It is omega of n squared. It's false. It's correct. Something here should be faster than n squared. Right? Anybody has a guess? What should it be?
Big theta of n.
That's a bit too optimistic, because it will be more than n, because the first iteration, when I equals 1, the first iteration takes linear time. But then what happened to the other iterations?
They just take constant time.
It will take at least n time. I'm absolutely sure that it's at least omega of n time. Omega of n, because just look at this inner loop that happens when I equals 1. Inner loop when I equals 1. I'm running over j equals 1 to 3 all the way up to n. So it takes at least n time. As far as we know, it takes no more than n squared time, but it's somewhere in between. Any math students here, by the way? When I equal 1, what I get to the value of j? It starts with 1, then 2, 3, 4, all the way up to n. So I printed n auspices. I spent n time. Let's think about the case I equal 2. I equal 2, j start from 2, then 4, 8, 6, 10, all the way up to n. How many even numbers do I have from n between 1 and n? I have about n½ many numbers. But that's a number of even numbers that you have between 1 and n. It's n½ At which point you should yell, no, it's the ceiling or the floor of n½ actually, and the ceiling or floor. But in this course, we are giving very little respect to this sign, and we are giving very little respect to this sign. Trust me on it, they rarely influence the complexity. These two signs rarely influence the complexity, so just erase them almost in any case that you see. Unless they appear in the exponent of some algorithm and we really see one such case, you can ignore floor and ceiling. So if you allow me this little noise, everybody agrees that when I equal 2, how many stars do I print in the inner loop? n½ many stars, which takes n½ many time. So far I spent n plus n½ What about when I equals 3? J will be equal to 3, 6, 9, dot, 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 n. That is, it skips through all the numbers whose modulus 3 is 0. How many such numbers do you have between 1 and n? N over 3. Right? When I equal 4, then J will be 4, 8, 12, 16, n over 4, all the way up to I equal n. And this, when I equal n, then J will do exactly one iteration. So what is over one time? It's n plus n over 2 plus n over 3 plus n over 4 plus dot 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 n over n, which is n times, have you seen it before? This summation, 1 plus half plus third plus quarter plus all the way up to 1 over n. This is n ln n. How many people have seen it before? Just curiosity? Nobody. That's fine. We will actually use it in several cases, the harmonic sum. Why is it called harmonic? Because if you have a harmonic wavelength, I stole it from Wikipedia, then you can have a wavelength of length is 1 or half or 1 over 3 or 1 over 4, and so on, if the length is 1. Anyhow, the number inside the summation is exactly ln n plus tiny bit of noise, and there is n here, so it's n ln n. Well, it's not the place that you expected to see log n, I think. Okay, here's another example that we use all over the board. I'll pick some constant a. In this case, I'll pick a to be half. Not really relevant. For j equal 1 all the way to n, I point n stars. And now I'm doing n equals a times n. Well, think about it. Let's say that my house loses 10% each year. The value of my house depreciates by 10% each year. It means that the value of the house to start with is n. Then it will be 90% of n. So I'll use a, which is not 0.5 but 0.9. So n will be a times 90% times n in this example. And if n was 10, then after this iteration, n would be 5, then it would be 2.5, whatever it is when it's integer, and so on. Okay, and I do this iteration again. And I do this iteration again as long as n is larger than 1. And I'm asking again, what's a one-week time? And again, this is an example that appeared many times in this course. Before I changed n, when I just read n, but before I got to this command, how many stars did I print in this command? Exactly n. Then I'm doing n equals a times n. So how many stars did I print? A times n. Again, ignoring Florence Hill. And then I'm doing n equals a times n again. So in the next iteration, the third iteration, how many stars? It's a times the old values of a times the older values of a, which is a n. So it's a times n, a squared n. After kth iteration, you're printing a times k n. Right? It's if n equal half, then you start with n, then n half, n quarter, n over 8, n over 16, and so on. How many times do I execute this command before we are getting to this part? How many times do I execute this command? How many times do I execute this command?
N number of times.
Sorry?
N minus 1.
I start when n equals 10, 24, then a is 0.5. Then what is the next times that I execute n equals a times n, it will be 512, which is half of it. Then it will be 256, but and so on. Later it will be 16, 8, 4, 2, 1. So how many times this command is executed? It's not n. Log n. This command is executed log n time. If a is not half but different value, as long as it's smaller than n, then it's still log n time, order of log n time, just different base. Now let's see how many stars do I print. By the way, what happened to this code if a is larger than n? Just to see that you are alive. If a is larger than n, what's the running time? Infinite, of course. Let's see how many stars do I print, or what's the running time? What is n plus a times n plus a squared times n plus dot 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 a to the k times n? It will stop at some point. N plus a times n, a squared n, all the way up to a to the, let's say the last iteration, a to the t times n, which is just n times 1 plus, if a is half, then it's the summations that you are getting there inside will be 1 plus half plus 1 over 4 plus 1 over 8 plus dot dot dot. That if a equals half. For arbitrary value of a, you're getting this summation. And here is an important trick. This loop does stop after log n time. But for the analysis, I'll say, you know what? I want to simplify the expression, so I let it add more and more elements over here because they are so tiny. You'll see in a second what I mean. So what is the overall running time? What does this sum equals to? That's geometric sum. Geometric sum for every a. 1 plus a squared plus dot 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 a to the t equals to 1 minus a to the t plus 1 divided by 1 minus a. And because laziness is such a blessed property, I'll say what happens when I don't stop at a to the t but just add a few more elements here all the way to infinity. Then this number of a to the t plus 1 disappears. And you're just getting, if you're going all the way to infinity, it is just 1 minus this number, which becomes 0. So it's just 1 over 1 minus a. So when a equals half, this number is 2. So the overall running time is order of a, no matter what is a. Cool? So it will appear multiple times, this example. Okay, just properties of big O. I'll let you figure out the details at home. If you have one function that runs in n squared, one function that runs in n squared, and one function that runs in n cubed, and one function that's running in n log n, then when you do the first one and then the last one, the second one, it's order of n squared plus n log n, which is just order of n squared. How do you prove it? Since I said that T1 over is order of G1, it means that I showed you the constant C1 and N1 such that if this is true, that's just shorthand to say this long sentence. And it's up to me to show you this constant, but they exist. Similarly, I can show you these constants C2 and N2 such that for any n larger than N2, this is whole. Which now means if I pick n to n prime to be the maximum of these two numbers, that is, this is true only for when we start from n being 100, this is true for n being 1000. So as long as I start when n being 1000, then T1 plus T2n are smaller than C1, that's for the definition, C1 G1, C2 G2. Let's take C prime to be just the sum of these two guys. So it's smaller or equal than C prime G1 plus C prime G2, which is just C prime G1 plus G2. Just a very tedious way to convince you that if you have one function that runs in n squared, one that runs in n log n, and you're doing both of them, total sum is n squared, order of n squared. Okay, and similarly, you have a function that is executed n squared time, but it calls in its inner loop another function that takes n log n time. It's n squared order of n squared time. You're calling another piece of code that executed n log n time. Then how many times you call everything? Order of n cubed log n. Kind of obvious. Okay. Next, we'll talk about Quicksort. Many of you have seen it. Many of you have seen it more than once. I hope that I can tell you new things about Quicksort, nevertheless. And along the way, we will do the analysis of Quicksort several times, and each time we will be more mathematically rigorous, but we need more tools that I'll introduce, in particular random variables and expectations. Quicksort is, the name is a bit misleading because it's algorithm that runs in worst case of n squared. So the name might be misleading for the first step. Great example of divide and conquer. How do I do it? I pick a pivot x, I pick some pivot x, and now I partition the array into all the elements that are smaller or equal than x. Then will be x itself. If x is a member, it doesn't have to be. But if x is a member, then x will appear. And here will be all the elements that are actually strictly larger than x. Correct it. It should be actually strictly larger than x. It's asymmetric. Here are elements that are smaller or equal than x. Here are elements that are strictly larger than x. So what is a divide and conquer thing about this algorithm is that after partitioning these elements, I call myself recursively on the small elements, call myself recursively on the large elements. And what is a merge? Nothing. The merging of the two pieces or the conquer just means, well, the moment that I partition these elements into this part, now if this is sorted and this is sorted, then the whole array is sorted. Okay, I'm here using the version that CLRS, the textbook, is using. It's a bit overly smart and less intuitive, but compared to different versions of partition. But let's talk about the partition algorithm. It takes the array A, and in the array A, I'm only caring about the part of the array that starts at index P and ends at index Q. Okay, so P and Q are indices inside the array. I'll pick the pivot as A to the P. I'll pick the pivot right now as the first element. And now what do I do? I'll keep the following invariant. After the pivot, I'll have a set of elements all the way up to index I, and all these elements must be at every step of the algorithm. When we start and when we end, and at every step of the algorithm. At this part up to index I, I'll have elements that are smaller or equal than x. Then I'll have a set of elements that are larger than x. And then I'll have elements that might be smaller or larger, I don't know. And that's the invariant that will be true when I start the algorithm, because when I start the algorithm, I is right here, and j is just the next element. So maybe I'll do a swap without really needing it. But let's see how I am making sure about how I am, as j will go, j will start from p plus 1 all all the way up to Q. J is the only loop that I'm using in the partition. J will go on, and I'll stop here only if I ran into, I want that all the elements from J all the way to the Y should be elements that are strictly larger than X. Again, I want all the elements from J all the way to the Y to be strictly larger than X, than the pivot. What happens if this is not the case? What happens if I ran into an element that is smaller than X? And in this case, I just ran into an element, AJ, that is smaller or equals to X. Small element, it should be in the left side of the element, not in the side of the big element. What's my invariant? Starting from element I, everybody that comes next must be smaller, must be strictly larger than X. So what do I do with this element? With element I first set I to be I plus 1 because I just found one new element which is smaller or equal than X. But I don't know ahead of time how many elements I have which are smaller than or equal than X. So each time that I run into one of these elements, I'll make a note, I'll increment I, and now what do? I swap AI and AJ. Small guy moves here, the large guy moves here, and I is I plus 1, right? Because now this element, I'm sure, is also smaller or equal than X. This element, I'm sure, is strictly larger than X. And J will continue from this point to the next one. Quick example, and please check it at home. Here is where I start. I'll pick the pivot X equals 6, that's I. J will be I plus 1, looking at the 10. And what happened to the condition of the loop? The if condition asks, is this element small or equal than X? The answer is that, no, it's larger, so go on. It's in the side of the big element. Next, 13. Smaller than X, no, so go on. It's in the side of the big element. Finally, find the mass. There is 5 over here, which should be in the side of the small element. It's smaller than the pivot. What do? I will set I to be I plus 1, because that's where I put the 5, and the 10 will go to the other side. Okay, I swapped the 10 and the 5. The I have been incremented. You have all the slides. You all know how to get to the PDF, right? You know in the Google document there is a link when you go to the syllabus. And I'll continue with J. This element is smaller than 6. No, it's fine. It's in the size of the big elements. 3, smaller than X. I find a violation. What do? I replace it with whom? With the 13. Replace the I and the J with the 13 and goes on. Yeah. Check out that it all works. You have the slides. But the idea, and it obviously takes linear time. How does a quicksort code looks like? Well, first, how do I call it? I called first call is there is some spelling mistake. It's quicksort of A start from 1 all the way to A, the whole array. Something that worth mentioning, worth mentioning in the code is that when I'm done with this code, I'll place the pivot at AI, where I will place a P and AI just to make sure that the pivot is right here. It's not crucial. And I is the value that I return. I will be where the last small element is. Again, I is where the last small element is. Okay. If the array is of size 1 or 0, they do absolutely nothing. To do is only to kill. If do something only if there are at least 2 elements in your array, And then what you do, you're performing the partition, and the partition doesn't, it's nice if it breaks it into two equal size parts, usually it will not. There are more smaller elements or more larger elements. So you're taking Q to be what the partition gave you, using the pivot as a first element. And now we're doing recursively quicksort over everything on the left side. Start from P, what was P, to start with P was 1. Start from 1 all the way to where the old pivot is, Q minus 1. You don't bug the pivot. And do a quicksort starting from the pivot plus 1 all the way to the R, which was when we start M itself. Everybody understand how it works? Any doubt about the correctness? Okay, and again, we are going through it in details because there is a lot of nice ideas to understand from Quicksort. So in the analysis, for simplicity, I'll assume that all the elements are all different. Don't have the same element that appears multiple times. And please stay focused because the analysis that I'm going to show is not the standard analysis that we're teaching with this algorithm. Not, okay, so T of n is the worst case running time. For example, that the worst case and the best case might be different. Okay, if you like recursive formula, then what is happening here? T of n is what? The runtime of n is what's the worst input? Somebody tried to help you and sort the array for you, which means that the pivot is always the smallest element. So the running time will be what I'm doing with, let's say, the left side, plus what I'm doing on the right side. But since the pivot was the smallest element, then in the right side, I will get the pivot right here, and everybody here is, of course, larger than the pivot, and there is n minus 1 elements over there. And actually, the partition did absolutely nothing. What will be the overall running time? I think that I have a slide. This is via recursive formula, recursion formula if you like it. If you don't like the recursion formula, then here is a straight explanation. Why does it run in n squared time? Because you did the partition once, and then you do the partition on the right side, which takes n minus 1 times the constant, of course. And then you're doing the partition on the right side. Now the right side is of size n minus 3 plus n minus 3 plus n minus 2, n minus 3. But next time it will be n minus 2, etc. And it's the same arithmetic sum that we have seen before. With n plus n minus 1 plus n minus 2 all the way up to 1. Read this sum from right to left. 1 plus 2 plus 3 plus all the way to n. We had it once today. It's theta of n squared. It's exactly no less than n squared, no more than n squared. So that's the worst case. That's if the input is sorted. Agrees? Everybody see where the n squared came from? And again, it's actually n squared over half, but half is a constant. We don't respect constant. So I told you that I'm a big fan of randomized algorithm. Quicksort is a great example where it works very well. What should I do for the quicksort? From this point down, it's exactly the code that we had before, so we're not going to discuss it. The only part here is that I'm trying to protect myself, partially protect myself against this case of input that is sorted, or pivot that is just the minimum. We'll understand the effect of it, but I'll pick k here to be a random number, random integer, between p and q. K is a random integer between p and q. Because k is some index of an element between p and q. And, oh, I have a typo here. Apologies. So I picked a random index between P and Q, and I'm going to pick the element at this index, A of K, and put it at the beginning. It will replace whatever was at X somewhere here, and pick this random element from the array and put it at the very beginning. A common confusion here is to say I pick a random value for the pivot. That's not what I'm doing. I'm not picking a random value for the pivot. I'm picking a value from the array. I'm picking a random index. Each element from P and Q has exactly the same probability to be picked, and this will be my pivot. And from this part, everything is exactly the same. Okay, what will be the running time right now? Before we are analyzing the running time of the randomized version, let's see what happens if I'm extremely lucky, and at each iteration, we split the array evenly. That is, the pivot that I picked is exactly the median. There is n half many elements smaller than it, n half many elements larger than it. Then the running time would be what? You're still doing the partition takes linear time, and then you're calling yourself on the left side, which has size n half. Well, it's n half ceiling over here, but ceiling and floor, you erase them. N half on the left side, n half on the right side. The solution to this recursion formula is that this running time is n log n. I already told you that I'm not a fan of recursive formula, so let's try to understand why the running time. In this very unlikely case that we are always picking the median, why this running time is n log n. And that's already some introduction into amortized analysis. Think about one of the keys of the array. And at some point the algorithm looks at me, and well, the algorithm looks at me, compares me to the pivot, and maybe move me to a different place. The algorithm spends a constant time for me to check and maybe move me to another place. And later on, the algorithm will compare me to another element, move me maybe to another place, and so on. But before I start the algorithm, I was part of an array, the partitioning. It was the very first partition that the algorithm looked at me, and then I was inside a big array of size n. So I was checked and maybe moved when I was inside an array of size n. Now we said that we are in this perfect position that the pivot is the median. So the next time that the algorithm looks at me, I'm inside a smaller array, right? Because the partition happens already. Now I'm inside an array of size n half. Next time I'm inside an array of size n over 4. Next time I'm inside an array of after k, if the algorithm looked at me k times, it means that I ended in an array of size of n over n, and half, n over 4, dot, dot, dot. If it did k times, then I'm in an array of size n divided by 2 to the k. The size of my array decreases exponentially. In the worst case, the size of my array decreased very slow. It was n minus 1 and minus 2 took forever. Now the size of my array decreases exponentially, so the number of times that the algorithm will move me from place to place is only log n. Now that was only for me, and I was one of n keys. So let's sum up the overall time for all the keys that all the algorithm is doing. So it's n times log n. Voila, that's great. Right? So I pay for every time that the algorithm checks me and maybe moved me, and I only needed log n dollars. That's the accounting method of the amortized analysis. And if every key has this part, then it's all good. But that was very unrealistic that I picked the median. But let's think about a bit more realistic question. Look at the array, and inside the array, I just put in colors. Here's the 10% of the really smaller, of the smallest element in the whole array. They don't necessarily appear in the beginning. The array doesn't have to be sorted if you really mix. But concentrate for a moment about the 10% of the smallest element, concentrate on the 10 percentile, the largest 10 percentile, and think about the median 80%. Not the very small, not the very large. I pick the pivot at random, one of the elements. What's the probability that I pick, no matter if the array is sorted or not, no matter how these colors are distributed, what's the probability that I pick a pivot that is in the smallest 10%? What's the probability that I pick a pivot, no matter how the array is sorted? Each element has the same chance to be picked. What's the chance that I pick a pivot in the smallest 10%? 10%. The probability that I pick a pivot that is larger than 90%, in the largest 10%, 10%. What's the probability that I pick what we'll call a good pivot? Good enough pivot will mean 80%, there is at least 10% smaller than the pivot, at least 10% larger than the pivot. What's the chance that I pick such a pivot? 80%. So 80% of the time I'll pick a good enough pivot, and bear with me 30 more seconds. What will be the overall running time in this case? If all the pivots that I picked are all good pivots, let's do the same type of exercise. The first time that the algorithm looked at me, I'm one of the kids, the first time that the algorithm looked at me, I was in an area of size n. Look at the first part, at the next step. The algorithm moved me into an array. If it's a very tiny array, then I'm happy. What is the largest array that the algorithm put me in? Given that I break the array in at least one, the smaller part will be at least 10% of the elements. The largest arrays that can be in the next part will be 90% of it. But maybe I'm in a smaller part, even better for me. I'll have to pay less. But the larger that I'll be in an area of size 90% of it. Next time that I'm moving, because I got good partition, it will be 90% of 90% of it. 90% of 90% of 90% of the way. How many times will I be transferred, even in the worst case? After 0.9 times n, my array becomes constant size. So I will be shifted from place to place, log to the base. Now it's not log to the base 2, it's log to the base of 10 over 9. 10 over 9 is 1.111111111. And log to the base 11 of n is just log to the base 2 divided by constant, log to the base 2 of 11, all smaller than a times log a. So the algorithm still, if I only use good partitions, the algorithm will still be n log n, which explains the quicksort, if you are picking the pivot at random. So it's n log n. But now what happens otherwise? Otherwise, even if I don't pick the pivots only as a good pivot, it means 80% of the time I pick good pivots, and the remaining 20% of the time I don't spend infinitely large amount of time. I'm still doing a partition, it just didn't change much. So sure, there is an overhead of not very efficient, not very impactful partitions that I'm doing, but they happen only 20% of the time. And 80% of the time, it's good partitioning, and so if I just charge all the effort to the good partitions, it will be n log n. And it starts to be cool. Okay? Now, to get an even better bound, please understand all of it. I'm available in office hours and on Zoom in other times. Just drop me an email if you say you don't understand something, and I'll be happy to revise it with you. Okay, so go over it, and for the next part, if you have other sources, remind yourself, if you've seen before, what are random variables and what is a term of expectation. I'll describe it in the beginning of the class, but if you'll get ready for it, even better. Thanks, everybody.